All right, today we're going to continue our exploration into looking at limits graphically and numerically. I want to remind you that we refer to the left limit, or the limit from the left side at c, to be expressed as the limit as x goes to c from the left side of f of x. And the right side, we do the same thing. We refer to the right side with a plus, and then the general limit, or sometimes I refer to this as the two-sided limit, carries no sign next to the c, and it exists only if the left and right side limits agree. So if these two numbers wind up equating to one another, then we get the two-sided limit. This is stating that in words, the limit equals the number if and only if the left limit equals that number and the right limit equals that number, where L is a finite y value. So we're going to talk a bit about how limits can fail to exist in these notes, and what I've done is I've set three descriptions of functions that have limits that do not exist. So in this case, the limit does not exist because the left side is different than the right side. And this expression here, y equals the absolute value of x plus 1 over x plus 1, if you were to graph this equation, what we get is this is a function that represents the value 1 that has been shifted left 1. So this function has a jump discontinuity. So there's a jump discontinuity. This is in our parent function toolkit, though we didn't get to this one this year because of pandemic days. But if we approach 1 from the left, or sorry, approach negative 1 from the left, we get an answer of negative 1. And if we approach negative 1 from the right, we get an answer of positive 1. This is a typo. This really should have been at x equals negative 1. So because my left limit does not equal my right limit, the limit does not exist. So there's a case where the limit failed to exist. Another example is unbounded behavior, and this is our reciprocal squared function. The reciprocal squared function has moved left 2 units. So visually, if we were to graph this function, we would have a vertical asymptote at negative 2, and we'd get our sort of Eiffel Tower shape going on next to that vertical asymptote. And so as I approach negative 2 from the left, my function grows without bound. Some people will say the answer is infinity. Some people will say does not exist. The limit does not exist. I like to say infinity because it does inform us a little bit more about what's going on. If I were to look at the right-hand side on the limit, I also get the answer infinity, or does not exist, depending which textbook you look at. Now, our limits appear to be the same values, but they're both infinite. And if we look at the more precise definition, it says the limit has to be a finite y value. So even though these are both infinity, we can't say they're the same infinity. They are not finite values. So the limit does not exist. So there's our second case where the limits fail to exist. We're looking at 3 cases. And the last one is a little bit harder to see. If we were to graph this function, sine of 1 over x, what's happening is as x gets closer and closer to 0, the period of the sine curve gets smaller and smaller and smaller. So we wind up getting these super rapid oscillations back and forth close to 0. And it's happening so rapidly that we're not approaching any specific value. We're basically bouncing back and forth between positive and negative 1. So this one, the limit as x approaches 0 of the function does not exist. And then if we're going to specify why, it's by oscillation. This is one of the least common ones for us to discuss in class, but it is a unique one, and it's worth talking about. Generally, our limits are going to fall in the category of being jump or a unbounded behavior. You could also have a case where the left side limit doesn't exist and the right does, but we'll see that. So example 1. Here we have a function defined as two pieces. The piece y equals x, which is a diagonal line, but we're only going to be defining it for x is greater than 1. Sorry, less than 1. So the only part of the graph that gets drawn is left of -1, +1. Okay. So that's the top piece. The bottom piece is a horizontal line at 3, 1, 2, 3, and we draw it from tree. So now that we've graphed the piecewise function, evaluating these expressions is pretty easy. As we approach 1 from the left, we get an answer of 1. As we approach 1 from the right, we get an answer of 3. Because these values disagree, the two-sided limit or the general limit does not exist. F of 1 does, however, exist. It's the closed circle. F of 1 is 1. And then the big idea that keeps coming through here is a function continuous? These four numbers are not the same. No. We could say the left limit does not equal the right limit. And specifically, this creates a jump discontinuity. We're going to explore continuity more in the next notes. Okay. Example 2. I'm going to draw the graph. Get an identity function that's shifted right 1 and up 2, so right 1 and up 2, and a sloping 1 line. We also have a parabola that has been shifted down 1, and we graph only the portion greater than or equal to 1. So the limit as we approach 1 from the left gives us a value of 2. As we approach 1 from the right gives us a value of 0. These two disagree, therefore the general limit does not exist. F of 1 does exist. It's the closed circle here at 0. And because our four numbers disagree, the function is discontinuous at x equals 1. It's a jump discontinuity. We can see that visually, or we could notice that the left limit does not equal the right limit. Okay, so those are the ways we can identify a jump discontinuity. Example 3, they've provided the graph for us. This is a straight line function with a hole in this. And if you wanted to see why we know this is a straight line function with a hole in it, if we were to factor the expression on the numerator, we get 2x plus 1. And we notice that the x plus 3 is a term that cancels. And so we should have the graph of the line 2x plus 1, which we do. Y-intercept of 1, a slope of 2, with a hole at x equals -3. 1, 2, 3, -3, there's a hole. So there's our factored expression, and if we were to evaluate limits, we would find, let's cross that out, we just did that up there. If we were to evaluate the limits from the left and the limits from the right, one thing that we could do is we could plug the -3 into this answer, or this equation, or we can look at our graph and we see 1, 2, 3, 4, 5. We get an answer of -5 in both cases. So that's hinting at how to solve it algebraically. If you did not know the graph, we can plug -3 into what's left behind. We get -6 plus 1 is -5. Revisiting tables, Here I have a limit expression, and what's in the box is always a mystery. For limits, in this case I told you it's an error, but we don't need to know what's in there to evaluate the limit. I noticed that the left side seems to be approaching a value of 3.4, and the right side seems to be approaching a value of 3.4. So the two-sided limit probably is 3.4. Now keep in mind, a tabular approach is not a very precise, perfect way to tackle limit problems. Likewise, a graphical approach is not a super precise, but usually good enough approach for us in class. The true way to evaluate limits comes algebraically or analytically. But for now, we're fudging. This looks like it's approaching 7. This side looks like it's approaching 7. So I would say the limit, the two-sided limit, is approaching 7. Okay. It could actually be like 6.9995, and our table isn't capturing that. But for what we have, that's the best we can do for now. All right. And finally, example 5. This should go pretty quickly. This is saying use the graph to shown at the right to show whether each statement is true or false. So let's deal with these one at a time. Does the left limit at A equal the right limit at A? Well, the left limit at A appears to be 1, and the right limit at A also appears to be 1. That is a true statement. So our first statement is true. How about this? Does the two-sided limit of the function at C equal 4? Well, when I look at C, we're looking at this location right here, the left side equals 4 and the right side equals 4. Because both sides equal 4, the two-sided limit is 4, and this is a true statement. All right, moving on to the next one. The general limit at B does not exist. Well, if I look at B, I see that the left side is about 0.5, and the right side is 3. The two sides disagree with one another, and because the two sides disagree with one another, the two-sided limit does not exist. Again, we have a true statement. The left limit at B does not equal the right limit at B, therefore the two-sided limit does not exist. Let's see if we get a false one here. Hopefully. The limit as x approaches C from the right is 2. So as we approach C from the right-hand side, we're getting closer and closer to that y value of 4. So this one is false. It should read, if we want to make it true, we would write the limit as x approaches C from the right of the function is 4. All right, and the last one. The limit as we approach B from the right-hand side is 3. So when we look at this graph, here is B. When we're approaching from the right-hand side, that's getting closer and closer to this y value, and that y value is 3, which is a true statement. Okay, that's the notes. Be sure to comment, like, subscribe, and have a great day.